Alright, our second unit is Unit 2, obviously, and it is going to cover kinetics. This is one of the really one of the big five things in AP Chemistry, which is typically covered during second semester, but I like to start off with it first semester, just to give you something a little bit challenging. My notes, when they aren't PowerPoint, will be kind of like this, where we kind of outline it. So Roman numeral 1 is reaction rates, and letter A is going to be types of rates. Then I'm just going to make up an equation. We're just going to say A reacts with B to yield C and D, just for some example purposes. So types of rates. The first one that we can talk about is average rate. When we talk about rates, it always implies some unit of time. Alright, I'm going to change this to caps. I think it's a little bit easier to read. Hopefully this year you'll be able to figure out my handwriting. It is atrocious and it's kind of strange with writing on a computer. It's a little bit different than writing on the whiteboard. So average rate. But rates are always over some unit time, some miles per hour. Usually with kinetics we talk about concentration per seconds. And we talked about concentration yesterday with molarity, and it is always, we use brackets in chemistry to denote molarity. Alright, so anytime you see brackets, it means the unit within those brackets is molarity or moles per liter. Okay, so average rates, we might set it up as rate equals, and we're going to do the change in concentration. So again, our brackets mean molarity. So we have our change in concentration up from time 2. This change is always time. I put a T1 there. My apologies. So really it should be T1 minus, or T2 minus T1. And we are going to put that over, really, T2 minus T1. So we have concentration at time 2 minus concentration at time 1 divided by time 2 minus time 1. Alright, so really we have change in concentration. So right now, divided by change in time. And then if we were to do the slope of that, just like rise over run, if we were to find the slope of a line on a plot of molarity versus time, that would give us the rate. Okay, so kind of just using a little bit of algebra and graphing. If we plotted concentration versus time, the slope would tell us our average rate. If our slope is steep, it's a really fast rate, and if we have a non-steep slope or a fairly gentle slope, our rate is slow. All right, so the steeper the rate, the faster the rate, and the opposite is also true. The second type of rate we can talk about is instantaneous rate. So really, instead of average or change in, the instantaneous rate is going to tell us the rate at a specific moment in time. Okay, so you might write instantaneous, and all that means is at a specific time or at a certain time. So if we want to know what the rate is after 15 seconds, we can get that. If we want to know the rate after 120 seconds, we can get that as well. Alright, and again, algebraically or graphically, it's represented by the slope of the tangent. Okay, so slope of tangent to the curve at time t. Now I'm going to insert a graphic from your book, and we'll take a look at that here in just a second. So from this graphic we can see three things. Our slope changes from left to right. It's a little more steep on the left, and then it flattens out at the right. And if we look at our three triangles, which again are perpendicular to our slope, our rate in the first one's 2.96 times 10 to the 5th molarity per second, and then we go to 2.09, and then finally 1.48. So as our rate progresses, our rate changes and gets less and less. Alright, the third type of rate we can talk about is the initial rate. So as soon as we put A and B together, what is the rate of our reaction? So really this is at time 0, or really it's the instant right after time 0, because at time 0 we probably haven't really reacted anything yet. So the moment we start reacting stuff is the time that we're looking at, or really the beginning of the reaction. And again, algebraically, this is just like our last definition, slope of tangent to curve at time 0. Okay, so slope of tangent to curve at t equals 0. And the last thing for tonight's notes is really what you covered with the group project you did in class today. That's what you should have gotten out of it. But there's a stoichiometric relationship, or maybe a stoichiometric rate comparison that we can do based on our balanced equation. Again, this is just a recap of what we did in class. So stoichiometric rate comparisons. I'm just going to again come up with an equation. We're going to say magnesium chloride reacts with sodium hydroxide. Put a couple lines for our coefficients. And these two things yield sodium chloride and magnesium hydroxide. Alright, so sodium chloride and magnesium hydroxide. And to balance this, if we kind of look at our equation, just quick balancing, we've got 1 Mg on the left, we've got 1 on the right, we've got 2 Cl, so we need to put a 2 over here. I'm going to erase that and just make it a different color. So I have 2 chlorines on the left, we only have 1 on the right, so we're going to need to make it a 2. Alright, and then we have 1 Na on the left, we've got 2 on the right, so we need a 2 in front of sodium hydroxide. And we've got 2 hydroxides on the left, and we've got 2 on the right. Okay, so that's a balanced equation. We could put some 1s there in front of our 2 magnesium compounds, but we're not going to worry about that. So it's a 1 to 2 to 1 to 2 ratio. So if we were to determine the rate of, let's say, the disappearance of magnesium, or the appearance, I'm sorry, of magnesium hydroxide. So the change in concentration of Mg, we'll do chlorine. Alright, so magnesium chloride. So change in concentration of magnesium chloride over time. And because it is a reactant, its change is going to be negative. Okay, because what happens to our reactants as they react? Their concentrations become less and less. And what happens to the concentrations of our products? They become greater and greater. Okay, so if we know the rate of magnesium chloride at some negative value, the rate of sodium hydroxide, alright, because of the stoichiometric relationship, because there's twice as many moles of NaOH as there are magnesium chloride, its rate must be twice as fast, or in this case, negative 2 times as fast. Alright? And again, these are both reactants, so they have negative rates. Their concentrations are getting less and less. In this graphic, again, 2 things are evident. Molecule A is our reactant, while molecule B is our product. So really our slope of A is a negative slope because we're getting less and less product, okay, and the rate is slowing down negatively, where B, our rate slows down, but it's a positive slope because our concentration is continually increasing. And this is a good graphic of what we're going to see in this next little section. And then if we compare these to our products, so if we compare it to magnesium hydroxide, the rate of what we call formation of magnesium hydroxide is equal to the rate of magnesium chloride's disappearance. Okay, so they are just opposite signs, but the same rate. And then the other thing we can equate this to is the formation of sodium chloride. So again, concentration, we do our brackets, divided by change in time. So it's a rate because we're dividing by time. And it's going to be positive 2. So its rate is twice as fast as the rate of the formation of magnesium hydroxide. How come? Because there's twice as many moles being formed. And that is pretty much your podcast for tonight. Alright? And I will see you in class tomorrow. Don't forget to summarize this with a couple sentences, and that is it.